I want to talk a little bit about the clock reaction lab and how rates of reaction can be explained at the molecular level. So the clock reaction lab is a great example. Well, it's first of all a perfect example of a nice chemical change where you can see the result. And it's also a great way to show how the concentration of a solution can change the rate at which the reaction will take place. So I've got a few visuals on the screen here, and I've linked everything to the Google Classroom for you. The first one is this really nice little graphic from compound chemistry. And in here you can see all of the explanations for what's happening here with regards to the collision theory. So you remember that from the last lesson, you need to be able to have lots of collisions between molecules. Those collisions need to be successful. So they need to have the right collision geometry with the right energy that's greater than or equal to the energy of activation. And when those are met, then the collision will actually be successful in that the reaction will go to completion. Okay, and there's ways to manipulate the rate, and you can explain all of those based on collision theory. So if you increase the concentration, increase the temperature, you'll notice that this little graph over here, I don't draw on there, but if you have a faster rate of reaction, you simply have more molecules able to collide with this correct collision geometry with the correct amount of energy, and you're going to actually have a faster rate. All right, surface area we're going to deal with in the next module. Increased pressure, that should make sense as well. We'll talk a little bit about that actually when we start our new unit on equilibrium, and then using a catalyst, how that works. So I thought that graphic was actually really kind of nice for you to see. All right, here we go. I'm going to see if this works as we go through, but this is one of the periodic table videos that goes over the clock reaction. I'm not going to watch the whole thing, but it's really interesting at the end because they slow the video down, and you can actually see the time at which the reaction actually goes from one to the other. What are we looking at here? We are looking at this chemical reaction right here, okay? So the clock reaction has to do with changing the concentration, but the mechanism by which these steps occur would be the same no matter whether you change the concentration or not. Changing the concentration will just manipulate the rate at which that reaction will take place. So for the clock reaction, you're looking at two different solutions. Solution A, we call it, and solution B. Basically, solution A has the source of the iodate ions. That's what you're looking for. When the iodate ions react with the starch, so your source of iodine in your starch, this is just one of those indicators. So iodine can be indicated to see if there's starch there. You may have done this in bio class when you did macromolecules. It's one of those famous biological indicators where if you're looking for a particular macromolecule, adding iodine will actually tell you whether starch is present. So for solution B, we have a solution that's got starch in it and some hydrogen sulfite. Okay, and then when the two solutions are mixed together, so I make them in huge volumetric flasks, and we simply put the two together. You can see that the starch solution actually looks a little bit cloudy at first, okay, and it is cloudy because of the starch in there. Imagine just taking cornstarch and adding it to water. It's going to be a bit of a cloudy solution, whereas the other solution that has the source of the iodate ions in it is completely crystal clear, so 100% transparent, colorless. Both solutions are colorless to begin with, okay? And then when you mix them together, you end up with a series of reactions. The one video that I'm going to post along with this module just goes to talk about the fact that in chemistry, oftentimes, there's not just one complete overall reaction, although you could summarize it that way, but they often occur in stages. And this is one where it's actually, you can kind of see that the molecules are moving, but you don't see that they're moving because it doesn't look like anything's happening until at the very end of the reaction. Then you're like, oh, clearly the molecules were moving and reacting, okay? So it's kind of a neat one that way. But you get reaction number one. Those iodates turn into some sulfates, and then you get reaction number two, and you're looking for this reaction number three where you get the dissolved iodine, okay, and it's going to be able to react with the starch to give this iodine starch complex That is what turns blue in the clock reaction. All right, so let's go over here and let's have a look at the video, see if it works and plays together at the same time.
The iodine clock reaction is a very famous reaction and very spectacular. A colourless solution suddenly, without apparently anything happening, turns very dark blue. Sometimes it even looks black.
Boom, there it is.
Now this is really neat because they slow it down. And it's really an inky blue-black color that you end up with.
It looks like magic. When my children were younger, I used to use this at magic shows at their parties, pretending I was a conjurer. They would say the magic word and bang, the solution would change colour. And they were really impressed.
Did you used to do lots of chemical reactions at your children's birthday parties?
Yes, I used to do chemical conjuring for every party. And nowadays it wouldn't really be allowed with safety laws. We had liquid nitrogen and all sorts of things. You have to understand that this is quite complicated, but it's not difficult. There's several different reactions going on at once, and that's why you get the effect. At the heart of the reaction, the blue colour is caused by triiodide, that is 3 iodine atoms with a negative charge, I3 minus, is interacting with starch. So in the solution there's some starch. And if you have I3 minus, then it interacts, and even a low concentration will give you a very intense colour.
Okay, I'm going to pause it there, but please watch the rest of the video if you'd like. In this chemical lab, we can actually just go back and be able to manipulate, right? Manipulate the actual concentrations, and then you can get different rates. And it's really fun. You can actually, like, be able to predict what would happen. All right, so we're obviously not going to be doing any of the calculations, although you could read through the lab to see what kinds of things you would have had to do. It would have involved doing some graphs, looking at reaction rate, and I just want to show you what those graphs would look like. So at the bottom of this lab, I've highlighted question number 7. I want you to do question number 7 and submit it. Okay, that's it. I just want you to be able to explain what's happening at the molecular level. So go back to your notes, make sure you've got all those key terms in there that we'd be looking for. This is one of the key things for this unit, okay? So I do want you to do that. But what you would do if we had written out the lab would be to look at, okay, here's our clock reaction observations and conclusions. As the iodate concentration increases, what would happen to the time, or the time of the reaction to take place? You'll notice that the time would go down, right? Less time for the reaction as you have an increased concentration. And so you show that where the concentration of the iodide is directly related to 1 over the time, the inverse of the time. And then how does that graph translate to the rate of the reaction? Clearly, as your iodine concentration goes up, the rate of the reaction would go up. So it's just looking at, all right, what's my unit of time for rate? And again, how do you measure that rate? Well, it could be any of the ways that we talked about in one of those modules before, right? Are you going to measure the rate of solution concentration going down per time? You got to have something per time, right? And it doesn't matter what it is to measure the rate. There's lots of ways you could do it. For this one, you just want to look at the overall trend. Okay, and what do you see? How do you summarize that? The concentration of the iodide is directly related to rate. So as the concentration of the iodide goes up, the rate of the reaction goes up as well. Okay, so that's it from that lab. And what I want you to do is answer question number 7, and if you could submit that. So basically it's explaining this lab at the molecular level. I've posted another really cute little TED Ed. And the TED Ed talks about, it's just a really fun little example of rates of reaction again. All right, we're almost done. Talk to you later.